Hi again, everybody, and thank you for joining us today for this webinar. This is one of in the series of our webinars, AI in Automotive. And today we're going to talk about the depth estimation challenge. This is actually a challenge that I assume most of you are common with and familiar with, just because you know the line of work and everything. And actually, we in our company, we deal with that on a daily basis in many of our R&D automotive-related projects. And actually, like we know, the different sensors, we're going to talk about them briefly today. And following that, we'll have a deeper discussion into stereo camera and the technologies around that. I have today with me Yoni Kasten. He's one of our 3D computer vision experts from the company. Yoni?
Hi.
All right. And then myself, Shmulik Shpiro, I'm the Global Business Development Manager in the company. So let's start. Okay, so basically, autonomous cars, how do they see the world? So like you can see on the lower left part, this is actually an image probably many of you are familiar with from 1957. So this isn't a newly dream, but it is something that many of the companies today are involved in it, and there's a lot of investments going on around it. Actually, I believe many of you saw just yesterday the Tesla announcement by the CEO, Elon Musk, that he said that they believe that full self-driving capabilities for hundreds of thousands of cars are going to be launched by the end of this year. So there's a lot going on. I know there's a lot of discussions. Is this actually going to happen now or later? Is it going to take less time or more? But we're not going to discuss that today. We're going to briefly go over, like I said, the technologies and dive into the stereoscopic one. But what we need actually to have these kind of autonomous capabilities is having a real-time obstacle detection system. And this system of these capabilities need to be activated and available in all weather conditions. That's a very important part, because we cannot have a car that will drive on this day, won't drive back from work if it's snowing or raining or something like that. And if we go a bit deeper than that, when we're talking actually of having the capability to do environmental analysis around the car and understand what's going on besides the car, let's say, all around it, to better understand what are the capabilities and how we can move forward. So this is just one slide. There are many like this. I just wanted to show a short example for how much is going on in the market. This is a slide of LiDAR manufacturers. So actually today, if I remember correctly, they count more than 70 companies developing different kinds of LiDARs, and LiDAR is one of the technologies that we're going to talk and available in the market. And estimations are that this market is going to reach over $100 billion in 2030. So that's the reason so many companies are running towards this. And this is a big thing. In many cases, or at least many believe, it's going to be the revolution of the next generation of cars. So a lot is going on. When we're talking about autonomous driving, so we have a few phases that actually need to happen again and again in a fraction of a second simultaneously, working on dedicated submodels, so we can actually perform the understanding of what's going on and give the right directions to the car. So the first one, the perception, is actually trying to understand what do we see around the car, what's going on, what are the objects around the car, to detect them, to classify them, to understand which one is more dangerous, which one is closer, more far away, and so on. And that's a basic stage. A lot of activities and efforts here, many using AI technologies, probably you are familiar with, and if you've been attending at least the last webinar, we spoke about that. And this is one stage that there's a big difference between different vendors and different kind of solutions and capabilities. The second phase is the localization, and this involves dedicated hardware and software as well. And basically, it's integrating the perception data with, I would say, very accurate maps to better understand exactly where the car is. It includes using things like GPS, IMUs, and many different kind of technologies to combine between the understanding of what's going on outside of a car and where exactly we are in a certain state. The second phase will be the path planning. Because we're talking about autonomous driving, so the basic first stage will be for the car or for the computer to design and decide what will be the optimal path from getting for this specific point where the car is right now and to the destination location. And this process needs to be processed and run again and again after each given time, because the data that comes in from the perception and the localization can influence these decisions and maybe change the path or alter it in a way or change the time estimations and so on. So this is the first stage, very important. And the last one, of course, the controls, is actually giving the commands to the driving controls in the car. Okay, so eventually something needs to move the steering wheel or tell the car to accelerate or stop or turn or blink or something like that. And that's the final stage. And as I said before, this is happening again and again and again all over the phase of the car is getting to its destination. So having said that, there are a few kinds of sensors that are available today and being used by the different vendors. I'm sure most of you are familiar with the sensors, so we'll go briefly over them. The first one is the optical one, RGB, what we just know as cameras. The second one is the LiDAR technology. The third is the radar, and the fourth one is ultrasonic technology. If you'll take a look at the slide, so it shows the positioning of the sensors around autonomous cars today. At least most believe it's going to be pretty similar in the, when we're going to get to the last stage, actually manufacturing, these cars and having them deployed everywhere, but in general, it should be the same. So you can see in most of these testing cars today, you'll see the LiDAR unit on top of the vehicle this way or in other different configurations. This way, in many cases, this will be a rotating one, giving a 360-degree coverage. You'll see the radar sensors along the side, and you'll see a smaller LiDAR unit in the front as well. Also, you don't see this on this image, but you'll have in many cars ultrasonic sensor as well on the back fender in most cases, just for going backwards, and parking the car. And one more sensor you'll have inside the car, that's the internal measurement unit, the IMU, more related to the positioning system, and so on. So this is a general array of how the sensors look when installed inside the car. Okay, so let's dive into the sensors themselves. Cameras. So I think the most important thing, and we know that, but to say about cameras is they're already around. Okay, so many of the cars today have cameras embedded on top of them. My car has actually is covered with cameras 360 degrees. Different kind of capabilities, of course. It's not autonomous, but I would say more advanced ADAS capabilities using these cameras. But this is a big advantage. They're already here. The pricing of the cameras are low, so there's no barrier using this technology getting into the autonomous driving cars. And of course, the best thing about the cameras is the resolution. So the good thing about it is that it's very good when we need to actually detect and recognize objects. And that's a main capability that being used today in the perception and understanding of what's going on outside of a car, but by the way, also inside the car today in many applications. So this is the leading one, and many believe that this will stay the leading sensor within the autonomous vehicle. Of course, the disabilities of these cameras are that they have limited capabilities in more severe conditions. Okay, so if we have low visibility, raining, snow, fog, things like that, they're a lot limited. Of course, if it's night, it's more complicated. So yes, we can add infrared cameras. Okay, that's a bit different, giving us more capabilities, but we're paying with a certain degree of resolution and things like that. So there is some kind of trade-off between using a camera and other sensors. The second sensor is the LiDAR, and of course, probably most of you heard about this. And this is actually using laser beams to calculate the depth of objects around the car, and it sends the lasers, of course, bouncing back, and we measure the time that it took to get back to the sensors. The good thing about this, it gives us a 360-degree coverage of a car. If we're talking about the rotating one that we saw earlier in the pictures, so it gives us a good coverage. It is very accurate, okay, and precise, and it gives us already embedded the depth estimation, so you don't need to extract that out of the data like you do in the cameras. We'll get to that later, and that's a good thing. And of course, it's a very robust technology. The disadvantage of the main one is the cost. So these systems are still significantly more expensive than regular cameras, and that's a challenge when we talk about cars and building thousands of cars and a lot more than that. And also, they have different kind of limitations towards weather. If we're talking about fog, snow, rainy conditions, so it will, in many cases, interact or interfere with the image coming and the perception coming out of that. So that's one thing to remember. The third sensor would be the radar. This is using radio waves actually to sense certain objects around the car. Once again, you can see on the right lower part of the screen an example of some kind of comparison between the LiDAR and the high resolution radar. So you can see one of the clear things is that the radar isn't that clear. Okay, the resolution is a lot lower than using a LiDAR or RGB camera, and that's one of the disadvantages. But the very good thing about radar technology is it's actually weather resistant. So it doesn't matter if it's raining or foggy or something like that, the radar we see through, at least in most cases. And also when you look at the pricing of the sensor, so it's positioned in a good place where it's not too expensive, and according to that, many manufacturers are actually embedding that in the solutions as well. And some of them at least believe that this is going to be a main sensor in the cars. I think one important thing to say is that no sensor is perfect. You know that, and you understood that. So you have here some kind of a spiderweb diagram showing a comparison between the different kind of sensors. But I think the details aren't interesting in this specific presentation. What is important is to understand that there needs to be some kind of a combined solution, and that's the path that most of the manufacturers are taking today. And the fusion is the solution, taking the good parts of at least 2 or more technologies, combining them, and then getting to very robust results and something that could actually give the needed capabilities in all weather conditions, and of course work in real time. So this was a quick brief of the different sensors technologies available in the market, and without taking more time, I'll pass the microphone to Yoni, which will dive into the main subject, into the depth estimation from stereo cameras. Yoni?
Okay, thank you, Shmulik. So as Shmulik said, I will talk about depth estimation from a stereo camera. And here is the outline for my part. I will start with a brief introduction for the problem. Then I will review some classic methods that do a depth estimation from stereo cameras. Then I will talk about end-to-end learning using deep learning. And we will see a glance to our next time webinar, domain adaptation. Okay, so depth estimation is useful for many applications like autonomous driving, drones, augmented reality, gaming, and robotics. And the basic question is that given a pixel, we are asking ourselves, what is the depth of this pixel? So from single view, we can only know the direction that this point comes from, but we cannot say what is the depth of the 3D point. But when we have two cameras and corresponding points between the two images, then each camera gives us a 3D ray, and the intersection between the 3D rays is the 3D point, and then we can tell what is the depth of this point. So here is an example for a depth stereo camera. Here is the right view, and this is the left view. Again, right view and left view. And we can see that the corresponding pixels between the two images have a large disparity where when the depth is small. But when the depth is large, then we will have small disparity between corresponding pixels. So actually, the problem of depth estimation is to find for each pixel in the left image a corresponding pixel in the right image, and estimate the disparity between the corresponding pixels. Then, given the calibration of the stereo camera, we can directly convert the disparity map to depth estimation. And we'll give a numeric example. Suppose that we have this correspondence and the pixels value of the points. Then in this case, the disparity is 50 pixels, and we will represent the number 50 as a red color in the disparity map. And if we take a point with a larger depth, then we will have smaller disparity, which is only 30 pixels, and we will represent it as a blue color in the disparity map. So we need to find for each pixel in the left image a corresponding pixel in the right image. And actually, we only need to search on this line, and we need to have some similarity measure that will help us to choose the right pixel. So the basic similarity measure called SAD, sum of absolute differences over the pixels in a patch. And actually, it measures the distance between two patches, two windows inside the image. So if the distance is low, we will get that the patches are similar. And if the distance is high, we will say that these patches are not similar. So this way, we can go over all the patches in the right image and choose the one with the smaller distance. Here is an example for the disparity maps computed only using SAD for different windows sizes. However, when we have a homogeneous area, then the SAD measure will give us similar results for all the corresponding pixels, so we will not know which one to choose. And as you can see in this example, on the left you can see the image, on the right you can see the ground truth, and in the center you can see that the SAD measure failed on these homogeneous regions. So how do we solve this? The assumption that most nearby windows have a similar depth. So we can use this to constrain the unstable areas. And this can be done using what is called a smoothness term in addition to the SAD measure. And you can see the result using belief propagation or graph cuts that can use the smoothness terms. The problem with this method is that they are really slow. SGM approach, which is semi-global matching, solves this by applying smoothness constraint only on one direction on the image, and this can be solved very fast. So after they do that for different direction, they combine all the directions together to get a consistent estimation of the disparity map. And here you can see the result. SGM on the bottom performs really well comparing to belief propagation and graph cuts, which are much slower than SGM. So this is a most successful classic approach. So the first method that used deep learning for depth estimation, published 4 years ago by Zvontar and Lacoon, and they treated the comparison between patches as a classification problem. So the input is 2 patches, and the output is whether they are the same or they are different. So in this case, the network should say that they are the same windows. And in this case, the network will say that they are different windows. So this is actually a classification deep network. So what they did is to replace the classic SAD measure with learned similarity measure, but the rest of the pipeline remained the same, meaning that they did the SGM optimization with smoothness constraint to get the depth map. And at the time of their submission, they ranked 1 among all the previous methods. And you can see that OpenCV SGBM ranked 9 at this time. And MCCNN actually had 2 versions. One of them was the accurate one, but the slower one. And they had a fast version, which was both accurate and even faster than the SGBM. And by the way, both methods are not fast enough for real-time application. And for example, this is something that we do at RSIP. We take an application and we make it run faster by constraining the algorithm to work well for the specific application. Okay, so what can be learned using deep learning? So the first thing, as we saw before, is to learn the similarity measure between patches. Another thing that can be learned is the smoothness constraint and the optimization part. So for example, for the SGM, we can learn how to set the parameters of the SGM using deep learning, or we can learn how to combine different directions of estimation using deep learning. Another thing that can be learned using deep learning is a post-processing, meaning getting an initial estimation and improve it using deep learning. But we will talk about end-to-end learning, which takes as input the 2 images and use a single convolutional neural network to get directly the depth from the 2 images. But the big challenge here is that Kitty, which is the most common data set, has only 200 pairs for training. So it's not a problem for patch-based network because one training sample has thousands of patch matches for training patch-based network. But for end-to-end learning, one training sample is actually one training sample. And it's not enough to train end-to-end network for stereo estimation. So the first method that did end-to-end deep learning for stereo was DispNet, and for this they generated a synthetic data set with images and their corresponding depth. And then they used unit architecture to estimate the depth directly from 2 RGB images. And they trained this network using the synthetic dataset. And here you can see a comparison between the methods at this time. DispNet, the end-to-end network, performs close to MCCNN, but both of them performed much better than SGM, the classic approach. However, DispNet was much faster than MCCNN. And here you can see the ranking at this time. At this time, MCCNN ranked 2, and DispNet ranked 4, but DispNet was much faster. By the way, today, both are ranked much lower because this is a very active research field. Another approach that we will review is GCNet. And if we get back to the traditional approach, we need to match a pixel from the left image to pixels on the right image. And usually, we define a range of disparities that we would like to consider between dmin and dmax. And then we can plot the cost for each disparity. And if we consider only this pixel, we can just use the winner takes it all selection, which take the selection with the minimal cost. But if we want to consider more pixels, then we can create a volume which its size is the height of the image times the width of the image times the number of disparities that we are considering, where for each pixel we store this matching cost vector. Then we can optimize the cost volume. So GCNet used this cost volume and they applied neural networks directly on this cost volume. And it was published 2 years ago by Kendall et al. And this was the first end-to-end method that ranked first on both Kitty datasets. And today they are ranked much lower, 43 and 100 on Kitty datasets. And here is their idea. They are getting the input images, they extract features from the images, then they concatenate the features into the cost volume without telling directly how to compare the features. Then they apply 3D convolutional neural networks to using a unit architecture, and at the end, they using differentiable winner takes it all, which is actually soft argmax, to get the right disparity and depth estimation. And you can see a comparison between GCNet and DispNet. And for the background pixels, they got much better results than DispNet. On the foreground area, DispNet was still better. But if we consider all the pixels, GCNet was much better than DispNet. But it is slower, and it can only perform 1 pair per batch because it requires much more memory. But in terms of convergence time, GCNet converges faster because it requires much less iterations to converge. So the last approach that I will review is GANet. And this is a very new method. It was published 1 month ago at CVPR 2019. And it is currently ranked 2nd in Kitty. And the nice thing about this method is that they used classic approaches inside a deep neural network. And here is their architecture. So first, they are doing feature extraction to the images and store it in a cost volume like GCNet. But then they have spatial layers called SGA, semi-global guided aggregation, which is a learned approximation for the classic SGM approach. And this helps them to globally find the right depth using the deep network. Then they have LGA, local guided aggregation layer, that improves the initial estimation of the depth. So this performs well, and I think that today this is the best way to go for depth estimation using deep learning. And here is some visual examples. This is the input image, and this is the result by GCNet, and the result by GANet. And blue means far away, red is closer, and green is very close. Okay, so again, GCNet and GANet. Here's another example, and the result by GCNet and GANet. So you can see that GANet is much cleaner than GCNet. And the last example, this is the input image, result by GCNet and GANet. GCNet and GANet. But as we said before, this is a very active research field, and 5 new papers published at the CVPR last month. So it is very important to keep updated for the recent methods for depth estimation using deep learning. And for our next webinar, we will talk about a very important problem called domain adaptation. And the idea is that if you train a network on a specific environment, it's not trivial that this will work on a new environment. You train your network in New York, you want it to perform well in Los Angeles. And this challenge is very active research field, and we will talk about it next time. So thank you very much.
Okay, great. Thank you, Yoni. Thank you very much. So I hope everybody learned from this session, and Yoni went deep into the latest, I would say, methods to handle this kind of depth estimation out of cameras. This slide just show a handful of companies today that are actually working, developing, and manufacturing camera-based depth estimation solutions for the automotive industry. And I just wanted to give you some examples that this technology is actually being used in the market. And basically, this concludes this part of the session. We have more time, so let's see if we have a few questions from the audience, and we'll be happy to address them. And in any case, of course, if any of you is leaving, so we thank you for taking the time for this webinar. So let's give it a minute and see what questions are coming from the audience. Okay, so one question we have here is, can GENet perform in real time? Yoni?
Okay, so GENet with their accurate model is faster than GCNet, but it's not fast enough for a real-time application. But they have a real-time model that runs at a speed of 15 frames per second in a GPU. But this model is less accurate, but still much more accurate than DispNet that runs in a real time.
Okay, so I hope that gave the answer. Let's see what else we have here. We have a question: why deep networks work well for stereo matching?
Okay, so deep networks actually can capture semantic information from images. So as people, we know that if we see a car on the left image, we should search for a car on the right image, and the pixels should correspond. However, in the classic methods, such a semantic perception could not be used, but now with deep networks, it became possible. So that's the reason I believe they work so well.
Okay, great, thank you. Let's see what else we have here in just a second. Okay, so we have here, can you show the images again? Which one? Or are these any cases that GCNet achieves better accuracy? Okay, so just a second, let's go back maybe, yeah.
Okay, let's see the images again. So I think in this image, I would choose GCNet over GANet, because on the left part you can see that GANet smooths this barrier away, and for application of autonomous driving, I would like to know that there is a barrier here. So I think that sometimes GANet, although they're good at surfaces, sometimes they smooth out obstacles, and it's a problem for, especially for autonomous driving.
Okay, thank you. Let's take maybe 2 more, and then we'll complete this webinar. So we have here, how sensitive is GANet to different cameras?
So actually, they performed several experiments, and you can see the details on the paper. The most case that they're interested about is the Kitty dataset for which we took the examples from, but they did other comparisons you can see in their paper.
Okay, and let's take one last one. Is there a model that can run in real time on the CPU? Okay, so that's a challenge always, right, Yoni?
Yes, especially for when you don't have a big GPU available. So actually, most deep neural networks solution are very good for using the GPU and very fast. But there is some, I will call it a classic approach from 2014, which is called Toast. And this work by Ranft and Strauss, which they did not use deep learning, but they optimized the SGM approach to be more accurate and more fast. And they perform well on the CPU, but their error is larger than the real-time version of GANet.
Mm-hmm. So I think it's clear that the best solution would be to have a GPU running in any case.
Yes, if you have GPU, you should definitely use deep learning approaches.
Yeah. Okay, great. So I see we have no more questions on the panel, and that's great. We're even ahead of time, so you'll have a few more minutes left for yourselves. And it's time to say thank you. So first of all, Yoni, thank you very much for joining us today and sharing all this knowledge and understanding of the field. We appreciate it.
Oh, thank you.
Okay, and thank you, the audience, everybody, for taking the time for this webinar. I hope you found it, educational and interesting. And please do not hesitate to contact us if you have any more questions. And we'll be happy to see you in the coming webinar on different kinds of AI in automotive topics. Thank you very much and have a great day.